The Claisen condensation is very similar to the aldol condensation, except that we're going to use an ester in this case instead of aldehydes or ketones. And this changes things because of instead of two R groups next to our carbonyl, we have one R group and one OR group, which we've seen before can act sometimes as a leaving group. So we now have a potential leaving group attached to our carbonyl species. So let's look at what happens when we mix this with. The first step is basically choosing the same OR group as our base. So if I have an ethyl ester, I'm going to use ethoxide as my base. If I have a methyl ester, I would use methoxide as my base. And we work it up with mild acid. So the first step is what you would expect. We're going to do a proton transfer, removing this hydrogen. And we form a resonance stabilized anion. I'm not going to draw the resonance for you, but you can do that. That is a resonance stabilized anion. And then what we're going to do is actually have that react with itself. Another ester that has not been deprotonated can serve as the electrophile in this alpha attack, or attack by the alpha carbon. And so we end up with, I'm going to put the ethyl over here. So there's my carbon that acted as the nucleophile. Let's identify that with a red dot. And then I'm going to have my carbon that I attacked. I formed an O-. And it's now a tetrahedral carbon temporarily. And we can observe loss of the leaving group. So I've produced ethoxide in this step through loss of leaving group. We've produced the new bond here, and again, let's just follow the red dotted carbon. And I drew that hydrogen there because now I hope you'll recognize that that hydrogen that I drew is doubly alpha. It is next to the ester carbonyl, and it's next to the newly formed ketone carbonyl. So this is a doubly alpha hydrogen. It's got a pK of around 9. And so the very next thing that happens, there's nothing we can do about this. The very next thing that happens is that that H is removed as a rather acidic hydrogen, and it forms a very stable anion, which has two additional resonance structures. I'll let you draw those, but basically you're just going to push the negative charge onto the carbonyl O. And this is where the reaction sits. And I can draw the byproduct. We made ethanol in this case. This is where the reaction sits until I add my second step, mild acid. And we'll protonate this anion that's formed. We'll protonate any ethoxide that's still remaining, and we will make our final product. And again, I'll put in the red dot so we can keep track of that carbon. You can see that the new bond right here is what is produced. And we've basically taken one of the esters, used it as a nucleophile, taken another of the esters, used it as the electrophile, lost OR, and formed the new carbon-carbon bond. Some points that we want to make about this mechanism. The ester that we start with must have two alpha hydrogens. And you saw that I removed two alpha hydrogens. Here's the first one, and if we want to follow that red dotted carbon throughout the reaction, there it is at the start. So we removed a hydrogen off the red dotted carbon. I made this anion. I used it as a nucleophile, made the new bond right here. Eventually I created ethoxide. That was the leaving group, and then it deprotonated a second time that same red dotted carbon. So here's your evidence that I need two hydrogens on the alpha carbon. If I only have one, for instance, if I had this molecule with one H there, I'll draw the H for you, that will not work so well in this mechanism. Why is that? Well, that's because when we get to this step, I don't have that second hydrogen. And so this base hangs around. We could actually do a reverse mechanism where we go backwards. And so this base can attack this carbonyl, reforming this tetrahedral intermediate. We could actually kick off the original nucleophile in a loss of leaving group step. So the fact that we can remove this second H and form this very stable anion, that's the driving force here. This is low energy. This is the driving force. If we can't take off that second H, we are unable to complete the Claisen mechanism, and so we won't get to the Claisen product that we have right here. Another point that we want to make must match the base to the ester OR group. So why do you think that is? So basically that means we can't use NaOH. Why can't we use NaOH, and must we use basically the equivalent OR group that we started with on the ester? Think about that. Remember from chapter 21 that esters can undergo hydrolysis under base conditions. That would be called saponification. So if we used a different OR group, we would swap R's at the least. If we used NaOH, we'd actually turn our ester into a carboxylic acid. It is possible, that's our desired product, but most of the time we want to maintain the ethyl part of the ester, or the methyl, or whatever we use for the final product. And so we're more likely going to choose a base that matches the ester, the R group of the ester. Okay, you remember we talked about crossed aldol reactions where we might produce up to 4 different products. We can also do crossed Claisens, and we can avoid those 4 products if we have certain conditions. So the crossed Claisen, one way we can do this, if one ester has no alpha hydrogens. So if one ester cannot participate as a nucleophile, we're much less likely to get undesired products. So let's look at that. We could have this ester where we have a phenyl group on one side, OR on the other. We could have ethyl acetate, as we saw on the previous slide. I could react them with ethoxide minus OET. I could work that up with H3O plus. And now I'm going to, again, I will put a red dot here. That's going to be the nucleophilic carbon. And I would get this set up here. The red dot was my nucleophile. That appears right there. You can see that I've created this new bond through my Claisen reaction. And I have no worries that this molecule here will react as a nucleophile because it has no alpha hydrogens. One other way to do that, use LDA first. So we don't have to use the strong base. We don't have to use the ethoxide base or the alkoxide base. We could use a strong base like LDA. It's a little more expensive. This is not going to replace the OR group on our ester because we know that this is not a nucleophilic base. So if I use LDA here, I know that I'm going to get a quantitative deprotonation at the alpha position. Then I can react it with another another ester in a crossed Claisen, and we would produce something like this. And let me mark my nucleophilic carbon again. And so you'll see that I have produced this bond right here has been created when this carbon attacked this carbonyl, formed the tetrahedral intermediate, and eventually eliminated OET. So I can make a crossed Claisen product this way, starting with LDA and avoiding the increase in potential products with a standard crossed Claisen, like we saw with a standard crossed aldol. Let's look at an intramolecular Claisen reaction. So if I can draw this large diester, and I'm going to go through and number the carbons here so we can keep track of them a bit better. So this is a 6-carbon diester, and I can react that with ethoxide as my first step, mild acid as the second step. What we're going to get is basically It's going to be either carbon 2 attacking carbon 6 or carbon 5 attacking carbon 1. I'll show you 2 attacking 6, but you can show 5 attacking 1 on your own and prove that you're basically going to get the same outcome. So let's look at carbon 2 being our nucleophile, and I will put a red dot there just so we can keep track of our nucleophile again. But this is going to proceed under the same mechanism I drew a few slides ago. Strong base removes one of the hydrogens on carbon number 2, that's the alpha carbon right here, and that's going to act as a nucleophile to attack carbon 6. So the question is, how big of a ring am I making by this arrow 2 to 6? And let me fix my arrows here. We should have that, and then I want to erase this other arrow. That's the arrow you can draw on your own. How big of a ring should I make in this case? If we count, 2 connects to 6. That's two pieces in the ring. 3, 4, 5. So there's going to be 5 carbons in the ring. Carbon number 1 is going to be a substituent on the ring. So I need to draw a 5-membered ring. And I can draw my substituent anywhere. Most of the time it's commonly drawn right there. I'm going to start numbering now. That's carbon number 1. This is carbon number 2. And I can number around the ring anyway. It doesn't really matter. So I'm just going to choose clockwise. 3, 4, 5, 6. And number 2 was the dotted carbon. So let's put a dot right there. I know that carbon 6 was the carbonyl. So I'm going to draw a carbonyl here. But first, this is making the tetrahedral intermediate. Then we remove ethoxide as the leaving group, reforming the carbonyl. Again, we're going to deprotonate carbon 2. You can see it has an extra hydrogen here. And the last step would be to reprotonate that, and we end up with a carbonyl there, a ketone. So we make a beta keto ester here. And that's going to be the product for any Claisen condensation, but in this case we've created a ring. And this is called an intramolecular Claisen. It does have a special name, Dieckmann cyclization, most likely named after the chemist who studied this reaction. And we're going to make ethanol as well as a byproduct. And if we started with 7 carbons here, we would make a 6-carbon ring. So you can make 5 and 6 carbon rings very easily. And later in this chapter, we're going to learn how to remove carbon number 1 altogether. So we could use this as a means of making 5 and 6 membered rings with a ketone already installed. Let's get a little more practice before we finish up this section. So let's produce these molecules via a Claisen. Draw them out, let you think about them for a few minutes, and then we'll talk about them. How do we make these via a Claisen? Alright, so we can start by drawing some arrows. We're going to fill in the starting materials and the reactants. Down here I can tell you most likely ethoxide is the first step, followed by mild acid workup on the top one as well. And I don't really know what base I want to use yet. But first thing I want to look at is the fact that we have a beta keto ester. So you can see the beta keto ester is still present here. That's a good indication that we used a Claisen to produce this. And we look at the ester as the nucleophile. So this carbon is our nucleophilic carbon. That means we're going to make this bond. And that means an OR group used to be attached here. So really what I'm going to do is redraw this 6-membered ring. That's my nucleophilic ester. And I can put a dot here, and I can put a dot here. That carbon is the nucleophilic carbon in this example. And then I have this piece, and it needs an OR group here. I'm just going to use ethyl. It doesn't matter what is here. That just makes life easier. Ethoxides are very common. And then, of course, it actually doesn't matter. Well, it does matter what OR group I use there. Let's use the ethoxide again. So that's might be how we parse apart. We'll call that problem A. Problem B, same thing. We have a beta keto ester. We're going to make this bond. This is our nucleophilic carbon, and it's part of the original ester on the right side. So let's just redraw that ester. And then I'm going to redraw the other part, the ketone, I'm going to give it its own OR group. And that's really all there is to that too. We would react these two carbonyls together. We have only alpha hydrogens here. We don't have any on this one. So we can do this crossed Claisen without fear of getting a number of different crossed Claisen products.